Hello everyone and welcome back. Last time we looked at AC circuits, and what I'd like to do to start with today is review what we did last time, and then today we're going to continue with AC circuits and look at something a little bit more complicated. Last time we looked at an AC circuit where we had a voltage source that had a form of V naught sine omega t. So what does this mean? Let's remind ourselves what this means. We've got a voltage source that, rather than applying a constant voltage as it would in a DC voltage source, we have a source that's oscillating back and forth. It's pushing one way in one direction, and then it pushes the other way in the circuit, then the first way, and then the second way. So we've got this voltage source that first will push one way, and then it will push the other way, back and forth and back and forth. So creating this oscillating voltage that's going to push current one way, then the other way, then the first way, then back the other way, back and forth, back and forth. So we have a voltage source with a voltage of the form V naught sine omega t. When we put a resistor in here, a resistor all by itself, we found that the current in the resistor, the current through the circuit, had a form of I naught sine omega t. When we put a capacitor in here, the capacitor all by itself, we found that a current was in the circuit of the form I naught sine omega t plus pi over 2, and I'll come back to this in just a second. And when we put this other new circuit element that we kind of talked about, the inductor, when we put an inductor in the circuit all by itself, we found that the current in the circuit had a form I naught sine omega t minus pi over 2. And then we had some relationships between the applied voltage amplitude, V naught, and the responding current amplitude, the I naughts, where omega, the resonant frequency, was equal to 2 pi f, the angular frequency was 2 pi f, where f was the ordinary frequency, f telling us the number of cycles per second, omega telling us the number of radians per second. Xc was then equal to 1 over omega c, where c is the capacitance and Xc is the capacitive reactance. XL was equal to omega L, where L was equal to the inductance and X sub L was equal to the inductive reactance. And then in terms of these phases, and I want to come back to this again in just a minute, the current in the resistor was in phase with the voltage. In other words, voltage, current, they go up and down together. So when the voltage pushes this way, the current is going that way. When the voltage pushes this way, the current is going that way. For the capacitor, the current in the capacitor leads the voltage by pi over 2. So if this is the current and this is the voltage, the current was in front of the voltage, always in front of the voltage. So at some points, even when the voltage is pushing one way, the current might be pushing the other way. So as the voltage starts to stop, the current is already going this way. And then the current changes when the voltage is a little bit out of phase. I don't know if I'm doing that right anyways, but I think you get the idea. They are not in phase. The current is always in front of the voltage by pi over 2 radians, a quarter of a cycle. For the inductor, the current in the inductor lags the voltage by pi over 2. So in this case, the current is behind the voltage, and the voltage is always in the lead by pi over 2, or 1/4 of a cycle. Very good. And then the relationships between the amplitudes, we had that for the resistor, V naught was R I naught, or in terms of the RMS values, V RMS was R I RMS. For the capacitor, V naught was Xc I naught, Xc, the capacitive reactance, or V RMS was Xc I RMS. And for the inductor, V naught was XL I naught, where XL is the inductive reactance, or V RMS is XL I RMS. Very, very good. What we want to do today, or what we're going to do today, is we're going to look at this circuit again, but we're going to put all three circuit elements in our circuit in series. A resistor, a capacitor, and an inductor. And we're going to see what happens. Let's just back up just for a second and think about what we're kind of doing conceptually. If you've ever read or studied anything about psychology, you might be familiar with the terms stimulus and response. in maybe a psychological experiment or something, the stimulus is what is done to a system or done to some object. The response is then, what does that object do responding to the stimulus? For example, I give an example in my class when we're all sitting together. I say, I might go to a student and say, hello, 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 student. And the student might say, stop that, don't do that. The stimulus is, me tapping, hello, hello, and the response is, don't stop that, don't do that. So stimulus and response. Well, we can think of this in terms of our circuit, where the voltage is what we do to the circuit, the stimulus that we apply to the circuit. The current is then how that circuit responds to the stimulus. We apply the voltage, the circuit responds, is the response then is the current. What does the circuit do? It has a certain kind of current. A big current or a small current? Well, that depends on the relationship between the stimulus and the response, which is over here. How are the stimulus and the responses related to each other? So what we're going to do is we are going to apply a stimulus to all three and find out what kind of response we get and see if we can figure out what's the relationship between those. Before we do that, I want to focus on one thing, and that is these, well, maybe I want to focus on three things, and that is these results over here. Let's just go over these one more time. The current in the resistor is in phase with the voltage. The current in the capacitor leads the voltage by pi over 2, and the current in the inductor lags the voltage by pi over 2. I want to write those down one more time, and I want to change them just a little bit. Well, I'd already written them down once, so I really didn't need to write them over again, so they're right here. But I want to change our perspective just a little bit. For the resistor, we have that the current in the resistor is in phase with the voltage. Well, I want to look at it in terms of the voltage. The voltage across the resistor is in phase with the current. Okay, they're both in phase with each other. The current in the capacitor leads the voltage by pi over 2. In other words, the voltage across the capacitor lags the current by pi over 2. So if the current is in front of the voltage is behind the current. So I'm just putting this in terms of where's the voltage. The voltage across the capacitor lags or is behind the current by pi over 2. And then the current in the inductor lags the voltage by pi over 2. In other words, the voltage across the inductor leads the current by pi over 2. So if the current is behind the voltage is in front of the current. The voltage across the inductor leads the current by pi over 2. Okay, very good. We just changed our perspective. Rather than where's the current relative to the voltage, where's the voltage relative to the current. Now, why did I do that? Well, we'll see in just a minute. Let's put those three elements in our circuit and see if we can figure out what's the relationship between the stimulus and the response. In other words, the voltage and the current. So here's our new circuit. We're going to have an AC voltage source that is then connected to a resistor of resistance R, a capacitor of capacitance C, and an inductor of an inductance L. This is sometimes referred to as an RCL circuit, AC circuit, because we've got all these three things RCL connected in series. Sometimes an LRC, RLC, doesn't matter. Typically just those combinations of R, C, and L to describe this type of circuit. Again, we're going to use the same polarity for our power supply. When our voltage is positive, that's going to mean the positive terminal is on the left side, negative terminal on the right side. Reverse that for a negative voltage. This is going to give rise to what we'll consider a positive current then in this direction. Here's our current, I, and our voltage, okay, V. Both time dependent. Voltage is going to be some time dependent voltage. The current, some time dependent current. Now, rather than defining our voltage as V naught sine omega t like we did last time, let's just think about this for a second. Let's try and make this easy on ourselves. In the last time when we were looking at all these things by themselves, we applied the same voltage, V naught sine omega t, and then we found out those different currents, and some of the currents were not in phase with the voltage. In this case, we've got a current, I, but that current is going to be the same current through the entire circuit. Whatever current we have is going to be the same current in the resistor, the same current across the capacitor, the same current through the inductor. The same current. We can't have different phases for the current. We can only have one current through the entire circuit. The voltages then across each of these elements will have different phases. Rather than defining one voltage, we're going to define one current that's going to be the same through the entire circuit. Then we'll figure out what's the phase difference for each voltage across each circuit element. So in this case, we're going to define our current as I is equal to I naught sine omega t. And then we'll figure out how are the voltages different, how are the phases of the voltages different across each one. We know some will be in phase, or the resistor will be in phase, one will be ahead, one will be behind. And then we'll add them all up to figure out what's the total voltage. And that's going to have some phase, we're not sure where. Will it be ahead of the current, behind the current? So we'll say that V is then V naught sine omega t. We expect it to have the same frequency, just like we found all the voltages and the currents had the same frequency last time. But we don't know what the phase of that final voltage is going to be. We will then just give it some arbitrary phase difference that we'll call phi. And one of the things that we're going to have to do is to figure out what is that value of phi. How are the current and the voltage out of phase? The applied voltage from the power supply and then the responding current. It doesn't really matter that we stick this in here rather than here. It's just going to make it easier for us to deal with a simpler form for the current that will be the same for each circuit element. All right, excellent. The next thing we did when we were looking at the signal elements was to apply the loop rule. So let's do that and see what we get.